So, we've just seen that it is enough to consider latent variables that are generated as Gaussian vectors with the covariance matrix equal to the identity. So now we're going to see the generic framework of variational inference. First, we're going to compute generic inequalities, and we will see afterwards how they can be used to solve our problem of finding the best set of parameters for the likelihood. Recall that the Kullback-Leibler divergence can be used as a metric between two densities P and Q. Its expression is recalled in equation 87. Now, we're going to introduce another probability distribution, which is Q lambda. We are going to see afterwards what Q lambda is precisely, but for now, let's just consider that Q lambda is a generic probability distribution. Two questions for you. Can you prove that the log likelihood can be written as elbow of Q lambda plus a Kullback-Leibler divergence where the elbow function is defined below? Besides, can you prove that the log likelihood is lower bounded by elbow of Q lambda? Assuming that the previous result holds, we have proved that the log likelihood is lower bounded by the elbow of Q lambda for any distribution Q lambda. The name elbow comes from the last inequality. It stands for evidence lower bound on the log likelihood. Recall that our original aim was to maximize the log likelihood. But it turns out that integrating the joint probability distribution in 93 is often intractable. So instead, we want to maximize the elbow. This is a fundamental idea in variational inference, maximizing a lower bound of the quantity of interest. You can now pause the video and try to prove the 2 points in this slide. The answers to these 2 points follow from the property of the logarithm, the Kullback-Leibler definition, and in particular the fact that a Karl divergence is always positive. So now, our aim is to maximize the elbow as a function of lambda and theta. A first manner to address this optimization problem is to iteratively optimize the quantity first in lambda, then in theta, and iterate this procedure until convergence. Here is a corresponding algorithm. First, you initialize theta and lambda. Then you find lambda, which maximizes the first expression. You update lambda accordingly and find theta that maximizes the same expression. You update theta and you repeat the procedure. Now, an exercise. Can you prove that this algorithm converges? You can pause the video. Assume that we are given theta t and lambda t, which are the results of t iterations of the previous algorithm. Then, according to the first step of the previous algorithm, 95 holds. Since the first term does not depend on lambda, we can remove it from the maximization, and changing the sign before KL leads to the minimization problem in 96. Here, we need to use an additional property of the KL divergence, stating that it is minimal and null when the two densities are the same. This leads to equation 97. Since the KL divergence is null between these two densities, the elbow function satisfies 98 after the first step. By definition of the second optimization step, we have the first inequality in 99, and the second equality comes from equation 98. Besides, by definition of the elbow function, 100 holds, and 101 holds because of the positivity of the KL divergence. Gathering 99 and 101 leads to the final results, establishing that the likelihood increases after each iteration of the previous algorithm. Therefore, maximizing the elbow increases the likelihood at each step. However, as mentioned before, it does not prove that the algorithm is going to converge to the parameter theta that maximizes the log likelihood.